In this video, we'll be looking at the graphs of some basic functions. Knowing the shapes of the graphs of these functions will be especially important when we talk about graph transformations in our upcoming videos. The first function we'll be looking at is the constant function. These are functions of the form f of x equals some number c. When we graph functions, remember, what we're graphing is y equals whatever the formula for our function is. So in this case, we're graphing y equals c. We've learned previously that equations of this form have graphs that are horizontal lines. We can also see that the graph is going to be a horizontal line because no matter what our input is, our output is going to be c. So for any x value as our input, the output or the y value will be c. For example, if I input 0, the output is going to be c. If I input something like 3, the output is going to be c. If I input a negative number like -2, the output is going to be c. So collecting all of these points together, you see that the graph will be a horizontal line. One thing to note about the constant function is that its domain is going to be all real numbers because we can plug in any input we want into this function and we'll get the output c. The range of this function is just a single element c because no matter what you input into the function, you'll always get the output c. One last thing to note about the constant function is that it is an even function because it has symmetry with respect to the y-axis. Our next function is the linear function. These functions are of the form f of x equals mx plus b. These are called linear equations because their graphs are lines. Because if you were to graph this function, you're graphing the equation y equals mx plus b. And we've learned previously that that's just a line with slope m and y-intercept b. So a linear function would look something like this, where the y-intercept is 0, b, and the slope of this line is m. The domain of a linear function is all real numbers because we can plug anything we want in for our input. And as long as our slope m is not equal to 0, our range of this function is also going to be all real numbers. The next function that we're interested in is the square function. This function has the formula f of x equals x squared. To help us draw its graph, we can always make a table of values. Let's look at the x values from -2 to 2. When we plug in -2, the output would be -2 squared, which is 4. When we plug in -1, the output is -1 squared, which is +1. When we plug in 0, 0 squared gives us 0. If we plug in 1, 1 squared gives us 1. And then when we plug in 2, 2 squared gives us 4. Plotting our points, -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. Connecting these points gives us the following graph. The shape of this graph is what we call a parabola. The domain of this function is going to be all real numbers because we can plug in any number we'd like into this function. As for the range of this function, looking at the graph, it looks like we have a lowest y value at 0, but then on either side, the graph goes up, so there's no upper bound. So our range is 0 to infinity. One last thing to note about the square function is that it is an even function because it has symmetry with respect to the y-axis. Our next function is the cube function. Its formula is f of x equals x cubed. Let's make a table of values for this function. Once again, let's look at the x values from -2 all the way to 2. If we plug in x equals -2 into the x cubed function, we get -2 cubed, which gives us -8. If we plug in -1, -1 cubed gives us -1. 0 cubed gives us 0. 1 cubed gives us 1. And then 2 cubed gives us 8. If we were to plot these points to draw the graph, we would get a shape that looks roughly like this. So this here is the shape of the cube function. The domain of the cube function is all real numbers because we can plug in any number we'd like and cube it. Looking at our graph, we see that the range of this function is also all real numbers because there's no lower bound for our y values and there's no upper bound for my y values. One last thing is that this function is symmetric with respect to the origin, so it is an odd function. On our next page, we'll look at a few more basic functions. Next, we have the square root function, which is given by the formula f of x equals square root of x. Let's make a table of values for this function to get a sense of what points are on the graph. This time, we won't be plugging in x values from -2 to 2 because we can't plug in negative numbers into the square root function. Instead, we'll look at x values from 0 to 4. When we plug in x equals 0, we get the output square root of 0, which is just 0. When we plug in x equals 1, square root of 1 gives us 1. Next, for x equals 2, the output is square root of 2, which we can type into our calculator to get approximately 1.4. For x equals 3, the output is square root of 3. Again, typing this into our calculator, we get a decimal, approximately 1.7. And then lastly, for x equals 4, the output is square root of 4, which is 2. So let's plot our points. We have 0, 0, 1, 1, 2, 1.4, 3, 1.7, and then 4, 2. Connecting these points here, we get the following graph. One thing to note is that the square root function looks like the square function flipped on its side. If this graph had a bottom half, then we see a parabola shape on its side. However, if it did have this bottom half, then this would not be a graph of a function since it would not pass the vertical line test. That's why the square root function just has the top half. Now, the domain of the square root function is 0 to infinity because we can't plug in any negative numbers into the square root function. And looking at the graph of this function, we see that the range is also 0 to infinity. This is because this point on the left here is the lowest point on our graph, which has the y value 0. And as we trace our graph to the right, the graph goes up indefinitely. That's why the upper bound is infinity. Next, we have the cube root function, whose formula is defined by f of x equals cube root of x. Again, we'll make a table of values for this function to get a sense of some of the points that are on the graph. This time, I'm going to choose the x values -8, -1, 0, 1, and 8. I picked these particular x values because I know that the corresponding outputs will be whole numbers. Now, when we plug in x equals -8 into our function, the cube root of -8 gives us -2. If we plug in -1, cube root of -1 is -1. For x equals 0, cube root of 0 is 0. For x equals 1, cube root of 1 is 1. And then lastly, when our input is 8, the corresponding output is cube root of 8, which gives us 2. If we were to plot the points and connect them, we would get a graph that has this shape. One thing you might notice is that the shape of this graph is very similar to the cube function, except it's flipped on its side in some way. We'll go into more detail about how the graph of the cube root function is related to the graph of the cube function when we talk about inverse functions. The domain of the cube root function is -infinity to infinity because we can plug in any number that we'd like into the cube root. Looking at the graph, we can determine that the range of this function is also -infinity to infinity. This is because when we trace our graph to the left, it goes down indefinitely, so there's no lower bound for my y values. And when we trace our graph to the right, it goes up indefinitely, so there's no upper bound for my y values. One last thing is that this graph is symmetric with respect to the origin, so this is an odd function. Our next function is the reciprocal function, and its formula is defined by f of x equals 1 over x. The graph of the reciprocal function looks something like this. The shape of this graph is called a hyperbola. Let's look at some of its features. If we start here on the graph and we trace to the right, our graph gets closer and closer to the x-axis. This is because as we plug larger and larger values in for x, 1 over x becomes a smaller and smaller fraction. So the larger our input becomes, the smaller our output becomes. That's why as we trace our graph to the right, the y values get smaller and smaller. We see something similar when we trace our graph to the left. Our graph gets closer and closer to the x-axis. This is because as we plug in larger and larger values in for x, the fraction 1 over x becomes smaller and smaller in size. The only thing that's different is that the fraction is a negative number. So as we trace our graph to the left, our y values become smaller and smaller negative numbers. So the graph gets closer and closer to the x-axis. Now, if we look at this portion of the graph and we trace our graph to the left, we see that the graph goes up. This is because when we plug in positive numbers in for x that get smaller and smaller, 1 over x becomes a larger and larger number. Similarly, if we're on this portion of the graph and we trace our way to the right, the graph goes down. This is because if we plug in a negative number in for x that gets closer and closer to 0, the fraction 1 over x becomes a larger and larger negative number. So this is the graph of the 1 over x function. The domain of this function is all real numbers except x equals 0. This is because if we were to plug in 0 in for x, we would have 1 divided by 0, which we can't do. For the range of this function, notice that if we're on this portion of the graph and we trace to the right here, the graph goes down indefinitely, so there's no lower bound for my y values. If I'm on this portion of the graph and I trace to the left, it goes up indefinitely, so there's no upper bound for my y values. So our range is negative infinity to infinity. However, there is one y value that we won't ever get. Notice that when we trace our graph to the right or when we trace our graph to the left, our graph gets closer and closer to the x-axis, but it never actually touches the x-axis. So there's no point on our graph that has the y value 0. That's why our range is all real numbers except for y equals 0. One last thing to note is that this graph is symmetric with respect to the origin. Any point that we have, if we draw a straight line through the origin, we have a matching point on the other side. Because it has symmetry with respect to the origin, it is an odd function. The last function that we'll look at is called the absolute value function, and it's defined by f of x is equal to absolute value of x. Let's make a table of values for this function. Let's plug in the x values from -2 all the way to 2. For x equals -2, the absolute value of -2 gives us +2. For x equals -1, the output is the absolute value of -1, which gives us +1. For x equals 0, absolute value of 0 is still 0. For 1, absolute value of 1 is 1. And then lastly, for x equals 2, the absolute value of 2 gives us 2. Plotting our points, we have -2, 2. We have -1, 1, 0, 0, 1, 1, and 2, 2. Connecting these points, we get the following shape. The domain of the absolute value function is all real numbers because we can plug in any number we'd like and take the absolute value. The range of the absolute value function is the interval 0 to infinity. This is because the graph has a lowest point at the origin, so it has the lowest y value 0, and if we trace to the right or trace to the left, the graph goes up indefinitely, so the upper bound for the range is infinity. And since our graph here is symmetric with respect to the y-axis, we know that our function is an even function. So in this video, we learned the shapes of the graphs of 8 basic functions. They are the constant, linear, square, cube, square root, cube root, reciprocal, and absolute value functions. In our upcoming videos, we'll be learning how performing certain operations will change these graphs.